Hello, I'm Patrick Emery from Matrix Science. In this presentation, we'll be looking at some of the issues associated with searching very large datasets and in handling the results reports.
Very large searches present a number of challenges. These are the topics we will cover during this presentation. The smartest way to merge files, like fractions from a Mudpit run, is using Mascot Daemon. Just tick the box at the bottom left. The batch can be peatlists or raw files. Note that Mascot Daemon 2.1 had a file size limit of 2 GB. This was lifted in 2.2 and we have successfully merged and searched a 6 GB file, although note that some web servers cannot accept uploads larger than 4 GB. If you don't want to use Daemon, you can merge peatlists manually. For DTA or PKL, you can download a script from our website. A nice feature of this script is that it puts the file name into the scan title, so you can tell which fraction a particular spectrum came from. The scan titles are displayed in the yellow pop-ups on the Mascot results report. As long as MGF files contain only peatlists, you don't need a script, just use copy or cat. If the MGF files have search parameters at the beginning, you'll need to remove these before merging the files. Because a number of third-party utilities add commands to MGF headers, and these caused a merge search to fail, Mascot Daemon 2.3 and later strips out the header lines when merging MGF files. In talking to Mascot users, it is clear that peatlist files are often much bigger than they should be. In other words, the peat detection is not very good. If you do a back-of-the-envelope calculation, you can see that 2 GB should be enough for approximately 1 million spectra. If you do intend to do a lot of large searches, it is worth getting the peat detection right. Shipping unnecessarily large files around wastes both time and disk space. 32-bit platforms have a maximum process size of 2 GB on Windows or 3 GB on Linux. To get around this limit, Mascot divides large searches into smaller chunks, so as to avoid having everything in memory at the same time. The parameters to control this are split number of queries and split data file size in the options section of mascot.dat. One consequence of splitting a search is that there is no protein summary section in the result file. This is not a problem because no one wants a protein summary report for a large MSMS search. However, some old client software gets confused by the missing section. The workaround is to increase the values so that large searches never split. Maybe setting split number of queries to 1 million spectra and split data file size to 10 billion bytes. This is okay, but remember to reset these values as soon as you are able to. Otherwise you might find yourself running out of memory or address space for your large searches. In early versions of Mascot, trying to display result reports for very large searches would often lead to problems with timeouts and running out of memory. To address this, the protein family summary loads most of the information on demand. This requires some index files to be created on the server, and these index files are cached so that the report loads much faster on the second and subsequent occasions. Proteins are grouped into families by means of shared peptide matches, and within each family, hierarchical clustering is used to illustrate which proteins are closely related and which are more distant. If there are 300 or more spectra, the protein family summary is the default. This is the appearance of a typical family report immediately after loading. The body of the report consists of 3 tabs, one for protein families, one for report builder, and one for unassigned matches. The report is paged with a default page size of 10 families. If you wish, you can choose to display a larger number of families on a single page. Proteins are grouped into families using a novel hierarchical clustering algorithm. If the family contains a single member, the accession string, protein score, and description are listed. If the family contains multiple members, the accessions, scores, and descriptions are aligned with a dendrogram, which illustrates the degree of similarity between members. The scores for the proteins in family 2 vary from 1,337 down to 73. In the earlier peptide summary or select summary reports, these would have been at opposite ends of the report. It would have been difficult to recognize that these proteins belong together, even though they have shared peptide matches and are all cytochrome P450. If you're interested in family 2, then you click to expand it to show the details. Immediately under the dendrogram is a list of the proteins. The table of peptide matches is similar to that found in the other result reports. Duplicate matches to the same sequence are collapsed into a single row. The columns headed 1, 2, 3, etc. represent the proteins and contain a black square if the peptide is found in the protein. Some matches are shared, but each protein has some unique peptide matches, otherwise it would be dropped as a subset. In this screenshot and the ones that follow, we've set an expect cutoff of 0.05 to simplify the picture by removing low-scoring matches. Moving down to family 3, the scale on the dendrogram is iron score. An HSP7C mouse and HS71L mouse join at a score of approximately 30. This represents the score of the significant peptide matches that would have to be discarded in order to make one protein a subset of the other. These two proteins are much more similar to one another than to GRP78 mouse, which has non-shared peptide matches with a total score of approximately 145. Note that, where there are multiple matches to the same peptide sequence, ignoring charge state and modification state, it is the highest score for each sequence that is used. Immediately under the dendrogram is a list of the proteins. In this example, because SwissProt has low redundancy, each family member is a single protein. In other cases, a family member will represent multiple same-set proteins. One of the proteins is chosen as the anchor protein to be listed first, and the other same-set proteins are collapsed under a same-set heading. There is nothing special about the protein picked for the anchor position. You may have a preference for one according to taxonomy or description, but all proteins in the same-set group are indistinguishable on the basis of the peptide match evidence. The table of peptide matches is similar to that found in the other result reports. Duplicate matches to the same sequence are collapsed into a single row. Click on the triangle to expand. The black squares to the right show which peptides are found in which protein. To see the peptides that distinguish HSP7C mouse and HS71L mouse, clear the checkbox for GRP78 mouse and choose Redisplay. It can now be seen that HS71L mouse would be a subset of HSP7C mouse if it was not for one match. It is the significant score of this match that separates the two proteins in the dendrogram by a distance of 32. That's the score of 55 for the peptide minus the homology threshold score of 23. You can cut the dendrogram using the slider control. If we cut the dendrogram at a score of 50, HS71L mouse will be dropped because it is now a subset protein. If you compare the matches to HSP7C mouse with those to GRP78 mouse, it is clear that these are very different proteins. They are part of the same family because of two shared matches, but many highly significant matches would have to be discarded for either protein to become a subset of the other. In summary, we can quickly deduce from the family summary that there is abundant evidence for both GRP78 and HSP7C mouse being present in the sample. There is little evidence for HS71L mouse. It is more likely that the HSP7C mouse contained a SNP or two relative to the database sequence. The family report also includes a text search facility, which is particularly important for a paged report. You can search by accession or description substring, or by query, mass, or sequence. Here, for example, we search for a peptide sequence. The display jumps to the first instance of the sequence, expands, and highlights in green the target peptides. The Report Builder tab is useful when you need a table of proteins suitable for publication. Let's assume we want to drop the one-hit wonders and only report proteins that have significant matches to at least two different peptide sequences. We open up the Filters section and add a suitable filter. Only proteins with significant matches to at least two sequences remain. The filtering is very flexible with lots of useful terms. Another thing you could easily do would be to exclude proteins from the contaminants database. The Columns section of Report Builder allows you to choose which columns to include and, if required, change their order. Once the list is filtered and the columns arranged as required, there is a button to export the table as CSV, which can be pasted into Excel and formatted to create a suitable figure for dropping into a publication. If you are still using Mascot 2.2, or if you have some application software that requires the results in the earlier format, and you are encountering problems with timeouts and running out of memory, here are some tips. Ensure you are using the Select report. If you're using a third-party client that has specified peptide summary or protein summary, add this to the URL before opening the file. &rep type equals select. Don't specify a huge number of hits just in case. Choose Auto to display all protein hits that contain at least one significant peptide match. &report equals auto. Get rid of the yellow pop-ups. &_show pop-ups equals false. Setting require bold red and an expect value cutoff will minimize the number of hits. &_ignore iron score below equals 0.5. &_require bold red equals 1. Note that the iron score cutoff is a score threshold when the value is 1 or greater. When the value is between 0 and 1, it is an expect threshold, which is often much more useful. I often set this to 0.5 to get rid of all the junk matches. If you can't remember these URL parameters, just click on the help link. What do we mean by standard scoring and Mudpit scoring? With standard peptide summary scoring, the protein score is essentially the sum of the iron scores of all the peptides assigned to the protein. Whether a duplicate matches to the same peptide, the higher scoring match is used. A correction is applied based on the number of candidate peptides that were tested. This correction is very small unless it is a very large protein, like here, or a no enzyme search. Despite this correction, as this example shows, when we have many low-scoring matches assigned to the same protein, we can still get a high protein score, even though none of the individual peptide matches are significant. A protein with matches to just a single peptide sequence is commonly referred to as a one-hit wonder and is often treated as suspect. This is actually a slight oversimplification. In a search with a large number of spectra and a small database, even though the peptide false discovery rate is low, a protein can pick up multiple false matches by chance. This is easily calculated using a Poisson distribution, where m is the average number of false matches per protein. In this example, m is 750 divided by 5,268, and we would expect 650 database entries to be one-hit wonders. However, 46 entries will pick up 2 false matches, and 2 entries will pick up 3, which could mean we report 48 false proteins. The problem isn't limited to large searches. It is the ratio between the number of spectra and the number of entries in the database that matters. So a small search against a small database can give similar numbers. To avoid this problem, we use Mudpit protein scoring, in which the score for each peptide match is not its absolute score, but the amount that it is above the threshold. Therefore, matches with a score below the threshold do not contribute to the protein score. The Mudpit protein score is the sum of the score excess over threshold of each of the matching peptides, plus 1 times the average threshold. For each peptide, the threshold is the homology threshold if it exists, otherwise it is the identity threshold. So even though a large protein like titin may pick up several random matches, with Mudpit scoring, the protein score is 0, so you don't see it listed in the report unless you specify a huge number of protein hits, as was done here to capture this screenshot. By default, Mudpit protein scoring is used when the ratio between the number of queries and the number of database entries after any taxonomy filtering exceeds 0.001. This default switching point can be moved by changing the value of Mudpit switch in mascot.dat. You can also switch between the two scoring methods by using the format controls at the top of the report. At some stage, it is likely that you will want to export the search results to another application or a relational database. If you want to write your own code, we provide a free library called Mascot Parser that provides a clean, object-oriented programming interface to the result file. The supported languages are C++, Java, and Perl. Mascot also includes a flexible export utility. If you want the XML format, you probably know that this is what you want. If you've no idea what XML is, chances are you don't want it. Choose CSV if you want to export to Excel. I'll show an example in a moment. Choose PEP XML if you want to export to Protein Profit from ISB. MZ-IDENTML and MZ-TAB are the standard formats from PSI for search result interchange. Mascot provides a very full implementation of MZ-IDENTML, and this is the one to choose if you are writing new application software that will use Mascot results. DTA Select is the tab-separated format used by Dave Tab's DTA Select program. The Mascot DAT file is the raw result file. If you need the result file for some reason and don't have FTP or SCP access to your Mascot server, this is a convenient way to get the file. MGF peak list is useful when you have the search result but can't find the peak list file. If you arrive here from one of the older reports, to begin with, you may need to select the required output format. Different formats have different options further down the page. To export to Excel, simply select CSV as the format and click on the Export Search Results button at the bottom of the page. In recent versions of Mascot, the report is prepared and then a Download button is displayed. In older versions, the download would start immediately. Once the download is finished, you can open it into Excel. Much easier and safer than screen scraping. For those of you into XML, here is a sample XML file. The schema is available from our website or your local Mascot installation. Please read the help for details. XML is ideal for transferring the results into a relational database. Even Microsoft Access can open the XML file directly into database tables. There is a very detailed help page for all of this, which describes how the export script can be called from the command line or a shell prompt as part of an automated pipeline. I won't go into details here, but this means that it is possible to set up a script that will, for example, automatically convert all of your Mascot search results into XML files. Figuring out the command line arguments from the help can be tricky, so in Mascot 2.3 we added a function to display the command line corresponding to the selected options. By the way, don't delete the original result files after exporting them, or you won't be able to view the standard Mascot reports in a browser.